Okay, guys, here we go again. We are focusing on empirical and theoretical probability from section 11.1. We need to get some definitions written down. Hopefully you have printed out your guided notes and you're ready to go. You're ready to fill them in. First of all, an experiment is a controlled operation that yields a set of results. We're all familiar with scientific experiments, and probability experiments usually involve things like flipping coins, drawing cards out of a deck, rolling die, things like that. The outcomes are the possible results that can come from an experiment. And an event is defined as a sub-collection of the outcomes. Now let's do, for instance, if my experiment is rolling a die, then just a regular die, excuse me, my phone is ringing. If my experiment is rolling a die, a regular die is going to have 6 numbers on it, 1 through 6. So my experiment would be rolling the die one time. The possible outcomes would be 1, 2, 3, 4, 5, 6. The event that I'm interested in might be rolling an even number. Well, if I roll one die one time, the even numbers that could come up are 2, 4, or 6. So out of the 6 different outcomes, half of them, or 3 out of that 6, are in the event I'm interested in. Okay, empirical probability. Empirical probability is the relative frequency of an event, like rolling an even number, based on actual observations of an experiment. So notice experiment and empirical both start with E. So empirical probability is basically my experimental probability. The empirical probability is what happens when you perform the experiment. Theoretical probability is going to be based on the number of ways we expect it to happen. Now, when I'm looking at empirical probability, the probability of my event, where the event is E, is going to be equal to the number of times that event occurs divided by the number of times you perform the experiment. Now, what I just talked about was not experimental probability. What I just talked about with the rolling the die was theoretical probability. Because we said, you know what, there's 6 different sides on that die. If I'm interested in an even number coming up, 3 of those 6 numbers are even. So the theoretical probability of me rolling a die would be that half the time I'm going to roll an even number. The number that I roll will be 2, 4, or 6. It's even. The other 3, 1, 3, and 5 are odd. That's theoretical probability. That's what we expect to happen. Now let's say I pick up my die and I decide I'm going to do an experiment. I'm going to roll that die 10 times. There's no rule, there's no force of the universe that means that 5 out of those 10 rolls are going to be an even number. I can roll my die 10 times and it come up 1 every single time. And even though I expected half the rolls to be an even number, none of them came out to be an even number. I didn't mess anything up. I just ended up on what we call a streak. Our theoretical probability and our empirical probability, or experimental probability, tend to match each other a lot better when we do a large number of repetitions. So let's get our definition down for theoretical probability, and then we're going to talk about the law of large numbers. The theoretical probability says that the frequency of an event is determined by a study of all possible outcomes. That all possible outcomes is what we call our sample space. What I was talking about rolling the regular die, my sample space were the rolls 1, 2, 3, 4, 5, or 6, because those are the numbers that could come up. To show the theoretical probability, instead of doing an experiment, I'm not doing an experiment, I'm looking at the possible outcomes, the sample space. When I do the theoretical probability, I'm looking at the number of outcomes, E, that show up in the number of possible outcomes, my sample space. That's where we got the 3 over 6, which reduces to 1/2 when I was talking about the die. Now, law of large numbers. This is important because probability statements only apply in practice to a large number of trials. A large number of times we repeat the experiment. They don't really apply to a single trial or even just a really small set of trials. The relative frequency in the long run is predictable. But like I just said, if you're just doing a very small number of trials, you can get a streak. You can get the same outcome over and over, and you weren't really expecting that. All right, some important probability facts. I've got 4 important probability facts, things that are going to help you as we study probability. The first thing that you need to be aware of is that if something is impossible, the probability of it happening is 0. For example, if I have a regular die, sides numbered 1 through 6, what's the probability of me rolling a 7 on that die? Well, there's not a 7. The probability is 0. That's an impossible event. On the other hand, the probability of an event that has to happen, that's a sure thing, is 1. So, if I'm rolling that die, regular die numbered 1 through 6, 1, 2, 3, 4, 5, 6, and my event is the probability of rolling a number less than 8. Well, what is the probability if I roll 1 die that the number that comes up on that die will be less than 8? Well, that's a sure thing. It doesn't matter what it lands on, that's going to be less than 8. So that is a probability of 1. All right, number 3. Since number 3 comes from these two, if the probability of an impossible event is 0 and the probability of a sure thing is 1, that means that every probability possible falls between that. 0 is the least possible probability of an event, and 1 is the greatest possible probability of an event. You can't have anything else. I can't say the probability of something happening is 2.3. That doesn't make any sense. If it can't happen, the probability is 0. If it has to happen, the probability is 1. And everything else falls somewhere in the middle. Because of that, could I have a negative probability? No. Negative numbers don't come between 0 and 1. The last important thing that we're going to list here is that if I add up all the ways things can go, the sum of the probabilities of all possible events is 1. So if I add up, if my events were rolling that die, 1, 2, 3, 4, 5, 6. The probability of rolling a 1 plus the probability of rolling a 2 plus the probability of rolling a 3 plus the probability of rolling a 4 or a 5 or a 6. If I add all those together, the sum is 1. Now there's one thing that comes out of that. If I say the probability of something happening, we're going to say A. And I add that to that, the probability of everything that's not A, that's the whole thing. So if A is rolling a 1, and this is not A, so this is rolling something not 1, if I add those two probabilities together, that counts of everything. Nothing is left out. And from that, we can say, therefore, the probability of not A is 1 minus the probability of A. So I just moved this probability of A to the other side of my equation. And remember, we can say not A as A prime or the complement of A. Okay, we got our definitions out of the way. Let's look at some examples. Empirical probability. Remember, my empirical probability is my experimental probability. When I defined that and I set up to show you how to calculate it, we said that our empirical probability, the probability of our event, is found by taking the number of times E happens, E occurs, and divide it by the number of times the experiment is performed. That's how I find my experimental or empirical probability. All right, example 1. We're at a music store in New York City. 46 people come into the store and they're selected at random, asked to choose their favorite type of music. And then it tells you how everybody answered. Well, what's the probability that out of those 46 people, I pick one that chose rock as their favorite music? Well, 12 chose rock out of 46. If I reduce that to a fraction in lowest terms, remember we did that on that review page, I find common factors. I can divide both by 2 because they're even. That will reduce to 6 out of 23. Sometimes probabilities in fraction form are difficult to look at. So I want you to go ahead and put 6 divided by 23 into your calculator. 6 divided by 23, and you get a decimal. Now this decimal is an approximate value. It's been rounded off because your calculator ran out of space. Let's write it down as approximately 0.26. Approximately, weigh the equal sign, 0.26. That's my probability that if I pick someone, they're going to favor rock. What about favors country? Well, out of my 46 people, 10 chose country. So that would be 10 out of 46. The number of times that event happened, pick country, out of the number of times we did the experiment. We talked to 46 people. Those are both even again, so that reduces to 5 out of 23. And when you put that into your calculator, you get 0.22 as an approximate probability. Go ahead and do the next 2. Okay, so we got our probabilities for each type of music, and then it tells you to add up those 4 probabilities. When we add those up, I am not going to use my approximate values that I rounded off because those aren't exact. I'm going to use fractions with common denominators. I can use either the denominator of 46 or the denominator of 23 because that's a common denominator. So the probability that they favored rock is 6 out of 23. Favored classical was 2 out of 23. Favored country is 10 out of 23. and favors something else is 20. No, 10. Sorry, 10 out of 23. When I'm adding fractions, I don't add the denominator. I just add the numerator. So I get 10, 20. What did I do wrong? 6, 2. That should have been 5. Favors country is 5 out of 23. See, I make mistakes whether I've got the video going or I've got you in class. 10 plus 5 is 15, 17, and 6 is 23. 23 out of 23. If I add up all the probabilities, I get 1. That was one of our 4 statements about probabilities on that last page. Let's do another example, another experiment. We've got people who went fishing. Friends went fishing, and it shows how many fish they caught. Find each probability. To figure that out, we need to know how many total fish were caught, how many times was the experiment performed. Remember, I'm using my calculator to divide the fraction. 13 divided by 55 is 0.24, rounded off to 2 decimal places. 3 divided by 55 is 0.05, rounded off to 2 decimal places. I'm getting my numbers from the chart. There are a total of 55 fish caught, so that's my denominator because this is empirical probability. If I add up each of the individual probabilities of all of the events that are possible, I get 1. I get everything. So this is what we were leading up to, something we already stated. The sum of the probabilities of all possible outcomes is always going to be 1. The probability of an event that is certain is 1. The probability of an event that can't happen is 0. So any probability of any event has to be between those 2 values. If I take the probability of A and everything that's not A, I get 1. Okay, let's look at page 3. The law of large numbers. We've already talked about the law of large numbers. This is what is the probability, the theoretical probability, that if I flip a fair coin, it will land on heads. Fair coin is any quarter that you happen to have in your pocket. It's got a heads on one side, tails on the other. It's only got 2 sides, and one of them is heads. So the probability that when I flip a coin, it will land on heads is 1 out of 2. Now, I want you to do this experiment. Find a coin. It does not need to be a quarter. It could be a penny. It could be a nickel. It could be a dime. But find a coin and flip that coin 10 times. As you flip the coin, write down H or T for heads or tails. So anytime you flip it and it lands on heads, you're going to write an H. If it keeps landing on heads, you just keep writing H's until you've done 10 total coin flips. Now, I'm going to simulate the experiment. I don't have coins, but I have my fake coins that I was going to bring to class for you. I've identified heads and tails by different colors. So if I flip my coin 10 times, I'm not doing a very good job, am I? Let's try actual flip. Woo! I'm getting lots of tails. There's 3 flips, 4 flips. That landed on tails. It landed off the screen. Oops, now I'm getting crazy. That one landed up on heads. 1, 2, 3, 4, 5. I finally got heads. Tails again is 6. You're doing your coin flip at home. I'm just giving you some data so that we can compare it. That's 8, 9, 10. Okay. Now I've got my numbers, you've got your numbers. We each flipped our coin 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have a list of heads and tails, I have a list of heads and tails, and they are not the same. Yours are different than mine because you did your own coin flips. Our probability is an empirical, an experimental probability. We did 10 coin flips, so our denominators are 10. Out of those 10 coin flips, count how many heads you had. I had 4. Count how many tails you had. I had 6. Now this is the part that's really hard because we don't have a class. Notice that I got close to half. This would reduce to 2/5. This would reduce to 3/5. Not quite half, but pretty close. I can pretty much guarantee you that at least one of you out there got something that was not close to half. The last time I did this with my class, and I'm going to give you this class data from my last class that I did this with, I had 190 tosses because I had 19 different people toss the coin 10 times each. Out of those 190 tosses in our room, 108 of those tosses came up heads and just 82 of them came up tails, which means that the probability of landing on heads came out to be 108 over 190. And if you put that in your calculator, it comes out to about 0.57. The probability of flipping tails would have been 82 out of 190 tosses, which came out to be about 0.43. Now that's not any closer than what I did in what I just calculated. If I do 2 divided by 5, that's 0.4. And if I do 3 divided by 5, that's 0.6. It's a little closer than what I got. It may be a lot closer than what you got, or you could have ended up with 50-50. Half heads, half tails. Generally speaking, the class probability is usually closer to that theoretical probability because of the law of large numbers. The law of large numbers tells us that the more trials or the more times you perform the experiment, the closer generally you get to the theoretical probability. Come back to that idea of streaks. I could have flipped my coin 10 times and got all tails. That would just be a streak. Okay, if you have a deck of cards, I recommend that you grab your deck of cards. If you don't, remember that there are 52 cards in a standard deck of cards, and those cards are divided into 4 suits. You have 2 suits that are red, hearts and diamonds, and you have 2 suits that are black. You got spades and clubs. So half my cards are red, half my cards are black. Since I have 4 suits, 52 cards divided into 4 suits, there are 13 cards in a suit. The different cards, you have ace, you have 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you have a jack, a queen, and a king in each suit. So you have 4 aces, ace of hearts, ace of diamonds, ace of spades, ace of clubs. You have 4 twos, a 2 of hearts, a 2 of diamonds, a 2 of spades, a 2 of clubs, etc., etc., etc. I want you to do the following example. Example number 1, it goes on to the next page, and I want you to find those probabilities. Remember, your experiment is that you're picking 1 card from a deck of cards. So you're picking out of those 52 cards, that's going to be your denominator. Pause the video, do the experiment, and then come back to me. If 4 of the 52 cards are 5s, all the rest of them are not a 5. So 52 minus 4 gives me 48 cards that are not 5s. There's just 1 5 of diamonds. Half of them are black. 13 of them, or a fourth of them, are diamonds. Kings or clubs. Remember, this is where we get into that intersection versus union. So this is why I encourage you to pull out your cards. One of those kings is a club. So you've got 13 clubs. That includes one of the 4 kings. So there's a total of 16 cards that fits in that union. King and club. There's only 1 card that is both a king and a club, the king of clubs. You got 4 aces, but only 1 ace of spades. Five or 10. Well, I've got 4 5s and 4 10s for a total of 8 cards. There's no overlap there. 5 and 10. There is no card in that deck that has both a 5 and a 10 on it, so that's an impossible event. Do you see another impossible event on that list? Hopefully you picked out that having a card that is both red and black is impossible. Do you see a sure thing, something that has to be? Card that is red or black. Yeah, every card in the deck is either red or black. Half the cards are red, and 13 of the cards, so a fourth of the cards, are hearts. Okay, probability example 2. Probability of having an S. You've got the letters for the word Tennessee. You put them on slips of paper. There are 9 letters, so there's 9 pieces of paper, and you put them in a hat. You're going to draw 1 letter out of the hat at random. Well, out of those 9 letters in the hat, how many of them are S's? 2. So the probability of drawing an S is 2 out of 9. If 2 of them are S's, how many of them are not S? Well, the other 7. How many of the letters in Tennessee are consonants? T, N, and S are consonants, so that's 5 out of the 9 letters in Tennessee. A T or an E, I can count 5. I've got 1 T and I've got 4 E's, so that's a total of 5 letters that fit that qualification. What's my probability of drawing a W out of that hat? Well, W is not in the word Tennessee, so that's an impossible event. What's the probability of me drawing a letter that's not a V? Well, none of those letters are V, so that's a sure thing. All right, example number 3. A family has 3 children. Consider the gender of each child. For example, MMF represents male for the firstborn, no, male for the youngest, male for the middle, and female for the oldest. How many possibilities are there? Let's figure out how many different ways this can happen. Order matters because it matters if you're born first, second, or third. So it's going to be permutations. Actually, it comes out to be kind of a fundamental accounting principle for me. That each time a child is born, I've got 2 options, male or female. So it comes out that there are 8 different arrangements for birth order. That first child is born, it's either a male or a female. And then the next child is born, and it's either a male or a female. And then that third child is born, still either male or female. So here's my ordered arrangement. Male, male, male. They're all 3 boys. So I'm going to write that one down. Male, male, male. Second one, male, male, female. Boy, boy, girl. Third, male, female, male. Fourth, male, female, female. And then write out the others where the first in birth order was female. So there's my 8 different ways that those children can be born with birth order. Answer the 6 probability statements after that. How many ways does it happen that there's exactly 1 female? Well, right there is exactly 1, right there is exactly 1, right there is exactly 1. So 3 different times there's exactly 1 female out of 8 different birth orders. Exactly 2 females. Well, there's exactly 2, exactly 2, exactly 2. So again, 3 out of 8 birth orders have exactly 2 females. What about no females? Well, just this one. all males. That's one way out of 8. 4 females? If I only have 3 kids, can I have 4 girls? No. That's an impossible event. Less than 4 females. Well, if I only have 3 kids, I'm guaranteed to have less than 4 girls. So that's a sure thing. At least 1 female. Well, only one birth order had no females. So for the other 7, there was at least 1. Okay, example 4. Now I'm tossing coins. I'm going to toss one coin 2 times. So 2 times in a row, I'm going to toss that coin. So when I toss it the first time, it's going to come up heads or tails. And then I pick it up and I toss it again, and it's going to come up heads or tails again. So my outcome, my sample space, is heads, 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 tails, tails, heads, or tails, tails. Those are the 4 possible outcomes in the sample space. Now let's look at these 6 probabilities. What is the probability that out of those 2 coin tosses, I got 2 heads? Well, that's that first one right there, one way out of 4. How about 2 tails? That one's right there, one outcome out of 4. What is the probability that they had the same outcome? Well, heads, heads is the same, tails, tails is the same, so that's 2 outcomes out of 4, or 1/2. What's the probability that I'm going to get different outcomes? Well, that would be 1 head and 1 tail. So that's 2 out of 4, or 1/2. What is the probability that I got heads on the second toss? Right? Oops, that's tails. Heads on the second toss, those 2. So again, 2 out of 4, or 1/2. And then at least 1 head. Well, I got 2 tails this time, so the other 3 have at least heads 1 time. All right, the last page of these notes are going to be geometric probability. I apologize, it's just a little fuzzy. Geometric probability. So I'm looking at the size, relative size of the sample space where I'm looking at area covered. This spinner, if I could spin it, has 4 sections, red, yellow, green, and blue. And they're all the same size. So my sample space is red, yellow, green, blue. The blue sector is 1 out of 4 equally sized sectors. So the probability the pointer would land in blue is 1/4, because it's 1/4 of the area of the spinner. Fill in those other probabilities. Pause the video, fill them in, and then start me back up. Now we've got a new spinner. This spinner is not equal. Blue takes up half the area. So are blue and green equally likely? Well, no, because that blue section is twice as big, so as likely as green or yellow. So if I thought about dividing it into 4 equal sectors, I would see that blue takes up 2 out of the 4, so blue takes up half the area. The probability of my spinner landing on blue, I said it and I wrote it wrong. The probability of landing on blue is half, because blue takes up half the area. What about probability of landing on blue or green? Well, that area is 3/4 of my spinner. Now I've changed it up a little bit. To figure out what this would be, think about dividing it into equal sized areas, so that you can think about how much each sector, each color takes up. If I make those equal size sectors, I would have 1, 2, 3, 4, 5, 6 of them. How many of those 6ths are blue? Well, 1, 2, 3 of the 6 equally sized sectors are blue, so that's half the spinner. Only 1 of them is yellow. Yellow or blue? Well, if 3 are blue and 1 is yellow, that's 4 out of the 6 equal-sized pieces. Not green. Green takes up 2 out of the 6, so not green would be 4 out of the 6. All right, guys, there you go. That's 11-1.